May I have your attention, please? The Energy Leaders Summit is going to begin shortly. I would like to ask all our distinguished guests to move into the hall and take your seats. We offer simultaneous interpretation service for this summit. Receivers are placed on your table, and please plug in the headphones and press the power button to turn on the receivers. Channel number 1 for Korean, channel number 2 for English, and channel number 3 for Japanese. Please scan the QR code on the page 3 of your handout and access a live Q&A in your app. Thank you. May I have your attention, please? The Energy Leaders Summit will begin shortly. I would like to ask all our distinguished guests to come into the hall and take your seats. And for this summit, we are offering the simultaneous interpretation service. The receivers are placed on your table. Please plug in the headphones and press the power button in the middle to turn on the receivers. Channel 1 for Korean, 2 for English, and 3 for Japanese. Please scan the QR code on page 3 of your handout and access a live Q&A in your app. Thank you. Good morning, ladies and gentlemen. We would like to begin the representative conference of BIXPO 2022 Energy Leaders Summit. My name is Min-hyang Jung, host for today's summit, and it is my honor to be here today. This Energy Leaders Summit is attended by CEOs and CTOs from each country to share the theme of 2050 carbon neutral strategy and future grid insights. Let me brief the overview of the summit today. The summit will begin with a welcoming speech by Vice President of KEPCO, Jong-hwan Lee. And a keynote speech will be followed by a Senior Vice President of the American Electric Power Research Institute, Neva Espinoza. And then there will be a panel presentation and discussion. Slido will be used during the live Q&A session. Please scan the QR code of your handout on page number 3, and you can answer the questionnaire and check the results right away in your app. First of all, Vice President of Korea Electric Power Corporation, Jong-hwan Lee, will make a welcoming speech. Please welcome him with a big round of applause.
Good morning, ladies and gentlemen. Welcome to BIXPO 2022 and Energy Leaders Summit. 반갑습니다. 에너지 분야 글로벌 리더분들을 모시고 오늘 이렇게 에너지 리더스 서밋을 개최할 수 있어서 아주 기쁘게 생각합니다. ELS에 참석해 주신 모든 리더분들께 감사드립니다. 특히 주제 연설을 맡아주신 니바 에스피노자 애플이 부사장님과 흔쾌히 좌장을 맡아주신 문승일 켄텍 석학 교수님께 깊은 감사의 말씀을 드립니다. 최근 글로벌 에너지 산업은 유가가 연일 상승하고 에너지 수급 상황 또한 악화하고 있어서 소위 에너지 쇼크를 겪고 있는 상황입니다. 앞으로 친환경 에너지로의 전환이라는 탄소 중립과 더불어 에너지를 차질 없이 공급하는 에너지 안보 문제를 동시에 해결해야 하는 쉽지 않은 도전에 직면해 있지만 국제사회가 지혜와 경험을 모아서 새로운 도약의 기회로 삼아야 할 것입니다. 빅스포 2022의 핵심 행사인 에너지 리더스 서밋은 2050 탄소 중립 전략 및 미래 전력망 예측이라는 주제로 탄소 중립 달성을 위한 차세대 전력망 구축에 관한 정책과 전력에 대한 전 세계의 움직임을 살펴보고 전력 산업의 미래를 예측해보는 중요한 자리입니다. 특히 우리나라의 경우에는 2050년 전력 소비량은 현재 2.4배 수준인 1258 테라와트 아워로 크게 전망되고 있어 재생에너지 확대에 따른 전력 계통의 유연성 확보는 물론 이에 따른 전송망 확충을 위한 주민 수용성, 또 막대한 재원 마련 등이 현안 과제로 부상하고 있습니다. 전력 산업계 글로벌 리더들이 머리를 맞댄 오늘 이 자리에서 인류 공동체의 생존과 발전을 위한 탄소 중립 여정에 있어서 수준 높은 이야기들을 활발하게 주고받으면서 서로가 가진 생각을 공유하며 현안 해결을 위한 슬기로운 대안도 모색해 보았으면 좋겠습니다. 빅스포 2022와 함께 해주시는 모든 분들이 이곳에서 유익한 성과를 거두시고 대한민국 광주에서 좋은 추억도 많이 쌓아가시기를 바라겠습니다. 감사합니다. Thank you very much.
Thank you. Now there will be a keynote speech by Senior Vice President of the American Electric Power Research Institute, Neva Espinoza.
Thank you. Thank you. Okay, well, thank you so much for having me here today. I'm very much looking forward to spending some time talking a little bit about what Dr. Lee referenced as the energy shock that we see going on around the world. So when we look at the entire energy economy and what we see happening, I think we all know there's just a ton of change. We heard yesterday from Arshad Mansour on what some of that change looks like and the significant contribution that we're going to see from the electric sector alone. Arshad talked a little bit about some of these big mega trends that we're seeing. Obviously, economy-wide decarbonization. And I'm going to bring us back to this economy-wide issue over the next 15 minutes several times. We talked a lot about climate resiliency and how we know weather is continuing to change and it's going to drive a need to change a lot of the things we're looking at with the electric sector. And much of that is going to be enabled by digital transformation. Pervasive sensing, significant internet capabilities, optimization of control systems, and a grid that is significantly smarter and significantly more modernized than it is today. Now, when we look at that, the one thing on this slide, if you're going to take away anything from this slide, I need you to look at the 3 words on the bottom: clean, affordable, and reliable. Because as we think about the role of the electric grid in our overall energy economy, while we achieve carbon neutrality, what we know is the role of that grid is going to increase, and therefore electricity is going to be a huge driver of economy-wide affordability and economy-wide energy reliability. Now, we know that's going to take a lot, and let's dive into a little bit of what that's going to look like. So 2030 is a decade of change. We've talked quite a bit about that, so I'm not going to focus on this. But what I do want to focus in on is some of the goals that are out there. And here I share what are the goals in the United States, and Arshad mentioned these yesterday, about a 50% CO2 reduction from 2005 levels by 2030, so in the next 8 years, followed by a reduction all the way to net zero by 2050. Now, you hear a lot that this is going to take new technology. And that's true, and that cannot be disregarded because it's very, very important. But it's going to take a lot more than just technology to achieve an economy-wide carbon neutrality. It's going to take new resources, it's going to take new capabilities, it's going to take new engagement with the customer and the overall community as we look at this. And there's not any one country doing this alone. We know that this is a global challenge. So here you see the US goals, and you can compare that to the goals in your own country. If we compare that to the goals in Korea, they're slightly different. They have slightly different numbers. Obviously, there's different resources. There's a different economy. However, it's the same end goal to achieve carbon neutrality by mid-century, and it has the same challenges. It needs the same new resources, it needs the same innovation, it needs the same capabilities that the US grid's gonna need and the European grid is gonna need, and the grids all over the globe are gonna need in order to enable this transition as we move forward. So one of the things I love about BIXPO, my first BIXPO adventure was in 2015, is the focus this conference has on innovation. The time it allows to spend in the expo to meet and collaborate and work with and network all of the different technology approaches that are going on out there. It is special and it is unique as part of this conference, and it's going to be something that helps us define and enable some of these goals as we move forward. Now, EPRI just recently finished a study that looks at, and these are US numbers, you got a QR code, you can scan it, pull out your phones. It's a publicly available document, you could all have access to it, but it looks at what is it going to take, or what could it potentially take, to actually achieve economy-wide net zero by 2050. And there's a couple things to note on this picture here. One is, on the left-hand side, you see 2020. What is final energy in the United States made up of today? And it's made up of electricity, some fossil fuels, a lot of fossil fuels, as you can see, and some low-carbon fuels. Electricity in the US makes up about 21% of the final energy in the US today. That number is not different from where you live. That number is a pretty global number. Most countries sit around 20% final energy being electricity. Dr. Lee talked about here in Korea, they anticipate that increasing by 2.4-fold. And here in the United States, based on the different technology options that may be available to us, we see the same thing. Electricity increases to 40 to 60% of final energy use. It is driving economy-wide decarbonization. It is the enabler in order to do it, and the grid is the leader. The electric sector in many of the places around the world is the first sector to start to reduce CO2 intensity, and is the first sector we see make huge strides and enable other sectors of the economy. So when we think about this final energy picture and we think about how much more important electricity is going to be as compared to today. And we all know it's really important today. What is it going to take to enable carbon neutrality, underpinned by a reliable and resilient electric grid? And I'm going to talk about 4 different core things. And there's lots of pieces, and there's lots of ways to slice this up and look at it. But the 4 things I'm going to talk about are, how do we reimagine the resources that are on the energy system? Because we have to look at this economy-wide. What are the new capabilities that are above and beyond what we have today, that are now more complicated and complex with all these new resources on the system? What does that mean for resiliency and adaptability when we know there's a changing climate? And what is the critical role of the customer in this energy economy as we drive towards carbon neutrality? So let's talk a little bit about those things and what those look like. The first is grid resources. The resources that are going to be on the electric grid globally are significantly greater than they are today. They are going to be more distributed. They are going to be more digital. They are going to hopefully be a whole lot more intelligent than they even are today. And that's going to enable this whole energy transition. So when you think about the economy, the energy economy, and if you're picturing in your head, let's do a little exercise, and let's picture something in our head. You have primary energy, right? Primary energy is fossil fuels. It's the sun, it's the wind, it's uranium, right? It is what is available to us here on Earth that we get energy from. So we take primary energy, and we take that energy and we bring it to an end use of the economy. Some of that is things like petroleum, right? That is an energy carrier, and we use it in parts of the economy. Almost all forms of primary energy are used to create electricity, and then electricity serves much of that economy as well. So although it's a relatively complex energy system, it's kind of simple in terms of how we run our global economy today. Now, our energy system of tomorrow is not going to be as simple as these one-line diagrams you may have in your head. It's going to be a whole lot more complex. It's going to have new resources and new players. And that's fundamentally driven by the energy economy that we know today is 80+% driven by fossil fuels in terms of primary energy, globally. Some countries have more, some countries have less. In the United States, it was more than 80%. It was close to 86% in 2020, driven by fossil fuels, the entire energy economy. So if we're shifting to an energy economy that now is net zero, we need to find ways to replace, manage, and mitigate CO2 that we're utilizing today. And that creates complexity. That creates new players. That creates new resources on this system. So I'm sure you're looking at this picture, maybe you're following the lines. Please don't follow the lines. The slide is designed to make your head hurt. So if your head is hurting a little bit, and this makes you a little dizzy, that is the intention, to really talk about the complexity of this energy system as we move forward. Now, if we simplify it a little bit more, that complexity is at 2 core things here. A huge part of that carbon management and mitigation, but what does that mean for the grid? Well, we've been talking about grid direct electrification for many, many years. And we all know over the next 10 years, the next decade, direct electrification of vehicles, of buildings, is going to be a key contributor to decarbonization. But when we look out beyond those 10 years, we bring in this concept of indirect electrification, creation of things like low carbon fuels, and that becomes a resource within this energy system. So what does that mean for the capacity build out? The resources, the kind of centralized and distributed resources we'll have on our energy system today. So we talked about final energy in terms of electricity goes from 20% to 2 to 3 times that. Well, in order to achieve that, the amount of capacity you need changes. It changes anywhere from 2 to 5 times the amount of capacity we have today, based on what other options are available, based on the ability to sequester carbon, based on the need for low carbon fuels in that energy economy. And so now this grid has a significant more amount of variable resources on it. It has highly renewable inverter-based resources on it, way, way higher than anything we have today. It has significant distributed resources, and we have to manage our demand a lot more flexibly than we do today. We have potential overbuild. So a lot of you may be thinking immediately when you see this, how do I build transmission for that? In the United States, building transmission is certainly not easy. I spoke to many of you over yesterday and last night, and I hear the same thing for countries around the world. So how do we transition our grid to be able to take this amount of capacity and these new resources on it? Now, totally different system, new resources. What are the capabilities that we need to make sure we have within that system? We're dealing with a lot of that today. So those capabilities, things like stability, things like flexibility, things like resource adequacy, are all going to be critical to that overall grid integration and what that looks like. And it's going to take more than technology to solve it. It's going to take new approaches. It's going to take new standards. It's going to take new operating practices. And of course, it'll take new and emerging technologies. But thinking about the system in a very different way, and a lot more maybe proactively than we have in the past, because we need to be designing our systems today for those that can support this totally different energy system by mid-century. So let's talk about an example, and we'll start with system stability. Right, so we all talk about inertia a lot. We understand that. We understand how the grid needs to respond as resources come on and off of it. But we fundamentally know that an inverter-based energy system or an inverter-based grid does not respond as quickly. It responds differently than a synchronous grid. Right, we know that. And this graph here shows you 20% inverter-based resources. So when we think about a system of tomorrow that is going to have significantly more inverter-based resources, we need to be thinking about ways now to get ready for that system. And some of those are operational practices, things like doing grid monitoring, real-time monitoring to understand what existing inertia is, setting inertia floors, redispatching for contingency, looking at real-time contingency modeling, and understanding when you may have to take one of your large assets off the grid and redispatch that model, so if you were to have a single point failure and a system and something falls off your system, you don't lose your entire system. Thinking about things more proactively and getting that monitoring and analytics in place in order to do that, managing the system differently. There's technical solutions too. Synchronous condensers you could think about. Things like synthetic inertia or virtual inertia, people like to call it different things, but the idea of using inverter-based resources like batteries, like solar PV, even like wind to some extent, with a lot of understanding of the complexities of that, to inject immediate frequency response in that overall system. We need to be thinking about and planning about that today. And we see these inertia constraints all over the world. They're not just in island systems anymore. They're not just in small systems anymore. They are in fully integrated systems, integrated grids that are interconnected in many places. We need to be learning from what we are seeing today, because the decisions we are making today around this energy system are going to impact how we are able to operate this energy system in 10 to 20 years. Let's talk about another key part, which is resiliency. So you can argue resiliency is a capability. I understand that. But it's too important to just put in that bucket. The climate is changing. We need to not just design our systems to be more resilient, but we need to think about our systems in terms of adaptation. When the climate changes, when the weather changes, how do I inherently design parts in my system to fail a certain way that I know I can recover from very quickly? It is a different way to think about resiliency, and it fundamentally adds more resiliency into our system when we add that in. And the last piece we have to talk about is the critical role of the customer. We've been talking about the customer engaging with our energy system for many years now. This is going to increase, and the customer is no longer going to just be a customer. They're no longer just going to be a stakeholder. They are going to become an integrated resource in our energy system. This is going to take a while, and there's the different pieces of this. But imagine a world where every water heater, every washer dryer, every appliance, essentially, not, is controlled, can be controlled by the grid. That every EV, from the charging stations from the very beginning, from the auto manufacturers, is installed with standards, internet capability, and load control capability in it. Each individual customer could potentially be somewhere between 2 and 11 kilowatts of load that you can control. Now, they have to be bought in. Rebates have to be part of that system. Codes and standards across the board need to be part of that system. And it's going to take significant partnerships, significant conversations across different parts, sectors of the energy economy, as well as with the customer base. So what's the value to the customer in this? And we'll pull up another example, which we'll look at potentially reducing overall energy costs. So if you go back to the beginning, we said that the amount of energy we use is now a lot more electricity. So a customer's electricity bill may actually go up by mid-century, but their overall energy burden can potentially go down, right? We know that there is a significant amount of efficiency gains just shifting from a gasoline vehicle to an electric vehicle. We look at things like here in the United States, the average household makes about $45,000 a year, somewhere between $40,000 and $50,000, and $8,500 of that goes towards energy. Just by shifting that household from 2 internal combustion vehicles to 2 electric vehicles, that family can save $2,000 a year, which is a significant amount of money for a $45,000, $50,000 household. So really understanding the complex benefits and the different benefits that are driven to a customer when they become part of a shared energy economy will be critically important as we move forward. So being mindful of time here, I'm gonna wrap up. You know, Arshad left you guys with, I think he said it was an African proverb, right? And he said that if you want to go fast, go alone. If you want to go far, go together. To achieve carbon neutrality economy-wide by mid-century, to create an electric grid that will enable that, it is certainly going to take us going together. It is going to be a decade of change. It's going to be a decade of new partnerships and a decade of collaboration that is going to enable our pathway all the way out to 2050. So thank you so much for inviting me here today. I very much look forward to hearing from our panel, and we definitely would love to hear from you as we spend the next hour and a half or so talking about what this potential grid of the future looks like. Thank you so much.
Thank you for your wonderful keynote speech. Next, we'll have a topic presentation and discussion session, and I would like to explain about how to participate in the Q&A. So you can participate in the Q&A by scanning the QR code on page 3 of your handout. So please open your handout and turn into page 3. Please take out your cell phone and turn on the camera app and scan the QR code, and let's practice some questions together. So first, please open your handout, page number 3, and take out your cell phone and turn on the camera app and scan the QR code on your handout. And let me ask your first question. Can you see the Q&A page on your phone? Yes? I hear some yeses, but I'm not sure if everyone's following me now. Are you ready? Because during the panel discussion, by doing this, you can actively ask questions and get the answers right away. So that's why we're practicing this in advance. So please scan the QR code on your handout with your camera. And are you able to see the first question? So let's look at the first question. What are you thinking now? Please be honest with me. So first one, just a cup of coffee. Second one, I'm missing my home. Third one, I want to drink soju. And last one, I want to take my socks off. So please check your answers. In 5 seconds, we're gonna check the results together. 5, 4, 3, 2, 1. Wow. Okay, so the number 1 is just a cup of coffee by 67%. But also, I'm missing my home section. The number is increasing there. So we can see the results right away. So let's practice one more question, and we're gonna move on to our next session. So let's look at the second question all together. What are your plans for tonight? What are you doing tonight? First one, I will enjoy special food of Gwangju. Second one, I will enjoy, it keeps changing. I want to drink soju and sleep early and save energy. Wow, it's related to our topic today. And I have no idea. So in 5 seconds, we're going to end the Q&A session, practice session. 5, 4, 3, 2, 1. Wow, the answer is sleep early and save energy. Very impressive. So thank you for participating. So next topic presentation and discussion session will be followed. The presentation will be under the theme of 2050 carbon neutral strategy and future grid insights. I would like to introduce the chairperson, Professor of Korea Energy Engineering University, Seung-il Moon.
Thank you so much. I really appreciate the wonderful, beautiful speech by the Vice President of the NEVA, Espinoza. And from your speech, we learned how important is carbon neutral. Also, we can recognize it again, how difficult it is. This is why we gathered together on today. And as far as I know, until today, about 139 countries declared carbon neutral until by 2050 around the world. However, the road to the carbon neutral is not a pavement highway. Many challenges, many obstacles are waiting for us on the way. Some of them seems, for me, desperately difficult to solve. Well, more than 50% of the energy should be supplied by electric power grid. The role of power grid became more and more important. This renewable energy, most of them should be generated from carbon-free source. As you may know well, the renewable energies are not predictable because it is highly dependent on the weather condition. And also, it is not AC, it is DC. Most of the energy from renewable energy will come out as a DC. Thomas Edison was right? We are going back to the 100 years ago. So let's take a look at our electric power system we have now. It has been designed and developed based on old technology. How old was that? More than 100 years old. Even though we have new equipment, the basic structure, basic idea are totally depend on the very old idea and concept. Also, it is very highly integrated AC system. This the integrated system has the inherent handicap to accept renewable energies in big scale. For secure and the resilient energy supply, we need a new, it's not new, totally brand new power network, the power grid. We have to adopt new technologies, new systems, and the new rules. How to prepare this road to the carbon neutral? This is the mission given to us. That is why we gathered together in this summit meeting today in this hall. The solution may not be unique. Each country has their own solution. Some country is leading, some country is behind. We already tried some the tasks. Some was successful, some was not. In this conference, we invite 5 excellent speakers from 4 different countries. In this session, we will hear from the presentation, and then we'll go for the Q&A. Let's welcome our speakers. Let me briefly introduce 5 speakers. The first speaker is Dr. Tran Ki Phuc. He is the director of Institute of Energy of Vietnam. Let's welcome Dr. Phuc.
Good morning, ladies and gentlemen. First of all, thank you very much, BIXPO, for inviting me here today at BIXPO 2022. On this occasion, we also congratulate BIXPO on its successful business in Vietnam power sector, especially on putting into operation Nghi Sơn 2 power plant, a BOT project with the installed capacity of 1,330 megawatts in August this year. Today, I'm going to provide you an overview of the Vietnam power system technology roadmap, which aims to achieve the target of net zero carbon emission by 2050. The content of my presentation includes modeling and targets, demand and resources, roadmap, and challenges. Let me start with the fact that at the United Nations Climate Change Conference in Glasgow, COP26, Prime Minister Phạm Minh Chính has pledged for Vietnam to reach net zero by 2050. In order to achieve the goal, the Institute of Energy has been assigned to review and adjust 2 master plans, the Energy Master Plan and the Power Master Plans, also called PDP-8, for the period 2021-2030 with the vision to 2050. In these master plans, 3 models have been utilized: the TIMES, the Balmoral, and the PSSE. The first aims to cover the whole energy system, and the second demonstrates a detailed representation of the power system. And the last one, the PSSE, as you know, describes the transmission grid. And as you know, it's similar to the one that Dr. Neva Spinoza has been presented here. A power development program has to meet 3 main targets: energy security, affordability, and carbon neutrality by 2050. You know, these targets reflect three aspects: demand, supply balance, economics, technology, and environment. And in some circumstances, you know, the crucial question is that which one is more important than the rest? And particularly energy security and carbon neutrality, which one is more important? Let's now have a look at demand and resources. You may know, in 2020, Vietnam power generation reached 239 terawatt hours, ranked 22nd in the world, 8th in Asia, and 2nd in Southeast Asia. The average growth rate of electricity demand during 2011 and 2030 was 9.5 per year. Overall, it can be seen that the electricity demand in Vietnam is expected to continue to grow rapidly, with an average growth rate of 9% between 2021 and 2030, and 4% annually over the next 20 years. I now like to draw your attention to the generation resources. According to studies from World Bank Group, GIZ, the IE, renewable energy resources in Vietnam may reach 700 gigawatt, which is large enough to meet power demand by 2050. For example, as you can see from this slide, Vietnam's solar power potential is around 350 gigawatt, and the onshore wind power potential is approximately 200 gigawatt. And you know, with 3,260 kilometer coastline, Vietnam has a large potential of offshore wind power, estimated around 160 gigawatt. Now, let's move on to the roadmap. Why technology roadmap? Somehow, you know, solar, wind, battery storage can be considered as technologies, whereas coal and gas are fuels. It can be said that energy transition is transition from fuels to technologies. Until PDP-8 is approved by our government, there are still several roadmap scenarios that are being considered, and one of them is illustrated on this slide. What I'd like to point out here is, first, renewable energy is account for more than 35% by 2030 and 60% by 2050 of total generation. Especially, offshore wind is planned to reach 7 gigawatt by 2030 and rise to 10-fold by 2050. Second, energy storage systems are critical to address the variability of solar and wind, you know. Therefore, an energy storage is planned to rise to 3 gigawatt by 2030 and 38 gigawatt by 2050. Third, coal. No more new coal-fired plants are planned in PDP-8, and no more new coal-fired plants will be added after 2030. And by 2030, overall coal-fired capacity will be limited to around 30 gigawatt. You know, phasing out coal-fired plants is critical. All subcritical coal-fired plants should be phased out by 2035. And for all unabated ones, they should be phased out by 2040. The remainder should be considered to be transitioned from the role of base load to operate with decreasing capacity factor towards 2050. And the process of retrofitting coal-fired power plants to coal-fired with ammonia should start after 2030. 4. Natural gas, is transition fuel, emitting 50% less greenhouse gases than coal. It plays a vital dual role of baseload and fast ramp-up capability. Therefore, by 2030, there will be around 15 gigawatt domestic natural gas firepower and 24 gigawatt LNG firepower plant. The process of retrofitting gas power plants to co-fire with hydrogen should start in Vietnam after 2030. 5th, CCUS. Coal and gas plants will be equipped with CCUS after 2030. And last, the 6th, power grid. Transmission and distribution grid is expanded to connect to renewable generation, especially by 2040, an 800 kV HVDC transmission line will be built to connect southern offshore wind generation center to northern load center. Clearly, there will be many uncertainties and challenges during the roadmap implementation. The biggest obstacle is that coal capacity replacement by renewable alone is not enough, Additional investment are required to overcome the variability of renewable. There are gas, energy storage, hydrogen, grid expansion, etc. Energy storage system. Battery storage, is still costly and has been used at limited scale. Pump station hydropower could be a feasible energy storage solution to enhance flexibility, but it is available only in certain areas, even in Vietnam. Hydrogen and CCUS technology are still at early stage of development and commercialization. What if CCUS fail? Those are just some of the key challenges. Many more can be found on this slide. And on that final note, that concludes my presentation. Thank you for your attention.
Thank you, Dr. Phuc. It was an excellent presentation, and we learned a lot. We know that how much the Vietnam government is supporting for carbon neutral, and the key uncertainties and challenges you just suggested is maybe many of the other countries have the same problem, including Korea. Thank you so much. The next speaker is Mr. Hiroshi Wani-san. He is the Vice President of Kyushu Electric Power Transmission and Distribution from Japan.
Good morning, everybody. I'm Hiroshi Wani from Kyushu Electric Power Transmission and Distribution Company in Japan. Kyushu is sometimes referred to as Japan's 10% economy. Relative to Japan's population, power demand, or commercial indicators, Kyushu represents roughly about 10%. However, as shown the graph on page 1, the amount of Kyushu's interconnected renewable energy represents about 20% of Japan. As the title of my presentation says, grid integration of large amount of renewable energy has been causing many problems upon maintaining stable power supply and power quality. I would like to introduce what kind of problems occurred in the last few years and how we have dealt with them. The amount of PV in the Kyushu area has been increasingly exploding. since 2012, reaching 11.8 gigawatt as of the end of September 2022. About 80% of the PV is connected to the 6 kV distribution grid. This increase is causing not only supply and demand balance problems, but also complex problems such as voltage flicker in distribution lines. We are currently working on 2 issues. The first is to maintain the quality of electric power. This is very simple. Since the amount of renewable energy fluctuates depending on the weather and time, its rapid expansion has brought various effects on power quality, such as the frequency and voltage of the power system. We took various measures to minimize this impact and maintain power quality. Please look at the illustration on this page. This is a supply and demand curve during a low demand period on a sunny day. During the daytime, the supply power greatly exceeds the load demand. So in order to maintain the frequency, the output of summer power is adjusted lower to maintain the balance. However, supply is still outstripping demand. PV output is curtailed. We have been curtailing PV output since 2018, which was also the first time in Japan. In order to maximize the use of renewable energy, we are working to minimize renewable energy curtailments. For stable supply for electricity, we have introduced a RE management system that can evenly curtail PV output. And we are ensuring the supply and demand management of Kyushu. And with expansion of solar interconnection, voltage flicker occurs during the daytime when the weather is fine and electricity consumption is low. As a result, the voltage in the distribution line fluctuates greatly, affecting consumer electronics. So we are working on preventing flickers by changing the settings of the PV PCS. The second is the effect to mitigate constraint to the power grid interconnections. Since the introduction of the FIT scheme in 2012, large-scale power system reinforcement work was required in various places, causing confusion, such as the burden of the large construction cost for power operators. Currently, transmission and distribution facilities are reinforced in accordance with the rule set by OCTO, and the confusion has been resolved. Also, the non-firm connection rule has been applied for the 500 and 220 kV bulk power systems starting from April 1st, 2022. Please see page 4. Next, we will look at our effort to maximize the utilization of renewable energy. These are efforts to minimize the energy curtailments in order to maximize the utilization of renewable energy. We implement 2 unique efforts. Firstly, we are striving to improve the accuracy of PV output predictions. By improving this accuracy, we can minimize the amount of residual energy when deciding the amount of output curtailments. Secondly, we are promoting the PV generators to switch to online control operations. Online controlled PV generators can immediately respond to curtailment orders, which allows generation to be in a better accord with the actual load dispatch. There are also efforts which are implemented nationwide in Japan. Firstly, there is online proxy curtailments. This is explained in more detail on page 8. Secondly, there is utilization of large-scale battery storage and pumped hydropower stations. Thirdly, there is the interregional cooperation to maximize the utilization of electricity outputs by exporting Kyushu's excess renewable energy to other areas by interregional interconnections. We can minimize the output curtailment in Kyushu. The second and third efforts have already been in implementation at my company. Page 5 and page 6 discuss our company's effort for improving the accuracy of the PV output predictions. Explanation will be skipped. Please see these slides for later references. We are also promoting the online switching of the PV generators. As of September 2022, approximately 70% of the PV generators who are not mandated to switch to online control have already been switched to online control. This allows us to determine the necessary amount of PV curtailment immediately before the dispatch. We can precisely determine the minimum amount of PV curtailment that is necessary. Please next page. Next, I will explain the introduction of online proximity curtailment. This is a system. Online controlled PV generators are curtailed as a proxy of the offline controlled PV generators and then compensated economically afterward. Due to constraints such as cost, it is difficult for same PV generators to switch to online control. Therefore, this online proxy curtailment system has the same effect as switching these offline control PV generators to online control. By introducing the online proxy curtailment, we can further expand the benefit of online control PV generators, allowing us to determine the minimum amount of necessary curtailment immediately before dispatch. We are planning to commission this system from December this year, and we estimate that we will continue the reduction of curtailments up to approximately 20%. Last, I will explain two efforts that we plan to implement in the future. Please reference afterward. Sorry. Both of these schemes are already in operation and will continue to be enhanced according to the ongoing requirements. I have picked up three main topics revolving renewable energy integration like this. That is all my presentation. I thank very much for your kind attention. 감사합니다.
Thank you so much, Mr. Wani-san. It is very interesting. The dot curve you showed us, I saw that in the technical papers, but it already happened in Japan, in Kyushu. And also the load curtailment is a big problem in Korea too. In Jeju Island, we have the same problem. The online proxy curtailment system you suggested is a very wonderful idea. I hope you can get a good result. The third speaker is Mr. Terry Donnelly, is the president of the COMED from US.
Good morning. I feel compelled to again offer my condolences to the people of Korea for the tragedy. I was there with my son in Itaewon Sunday night, and we had walked down the same alley at where the tragedy happened. We walked down that alley at 10 p.m. and the event happened at 10:15 p.m. So it's been a very emotional time for me and my son, and my heart is broken. I'm Terry Donnelly. I'm the president and also the chief operating officer of Commonwealth Edison, based in Chicago. We serve a population of about 10 million people. We were founded by Sam Insel, Thomas Edison's assistant, who came to Chicago from New York and pretty much invented the utility model of central station generation, the role of the regulator, natural economies of scale, and things like that, many of those things that are still with us today. So, what happened to the smart grid? We've seen a lot of vocabulary cycles in and out of our industry, but the term smart grid has risen higher and fallen more quickly than most. A decade ago was the buzz of the industry as we raced to invest federal dollars into predominantly AMI and distribution automation. So we set out to make the grid smart, and it's kind of like it was in the early 2000s with automobiles and optional upgrades. So we were kind of putting upgrades on the grid that we thought were options, like the automobile. In the early days, crank windows and heaters were all that was standard, and air conditioning and things like that were options. Well, now those things are standard. So smart grid and some investments, those are standard now. And we've seen the trend across the industry: smartphones, smart TVs. Smartphones may be becoming a phone. Smart TVs are still used, that term, but probably will be a TV as things become more standard. However, those technologies, smartphones, smart TVs, smart watches, the engineering can occur in modular steps based on standards that get upgraded. Our engineering challenges, the grid is not so easy. We lack many standards as we begin this transformation. We're figuring it out as we go, and it's like rebuilding the airplane while you're flying it. Has been the challenge, and pretty much literally we have to rebuild the power grid while it's energized. We've talked about climate change and high impact events. The only thing that I'm saying on this slide is gone is low frequency, right? That is gone when you look at the amount of events as they're listed here in the United States. And it's not just on the East Coast, you know, it's the Midwest, it's all over the country. Well, now smart grid has to go back to school. To build new capabilities that we heard about already. And DER adoption is a viable solution because of the growth in capacity, the economies of scale, policy initiatives, reduces prices, and it contributes to grid resilience, DER. But does it really? We say that, but it's going to be upon all of us to actually prove that. And I would say that we haven't yet proved it. That's our quest. So back to school is things like, I'll speak from my company and what our engineers are doing. Advanced sensors like distribution PMUs are being deployed on the distribution system through an algorithm of efficient placement. We also work with the Department of Energy on what they call the SIMPLE grant, which is Sensors with Intelligent Measurement Platform and Low-Cost Equipment. The PMUs are more the high end. We need something more inexpensive in that area, and we're working with the Department of Energy on that. We built a microgrid on the south side of Chicago that's 7 megawatts with solar on top of community housing and battery storage that's owned and operated by us, and an interconnection with a 10 megawatt microgrid at Illinois Tech, which is a university, which would make this the first utility operated microgrid cluster of 2 microgrids tied together at scale. We've deployed DERM systems in order to prevent overloads in high wind and solar areas, and we're deploying North America's first distribution linear state estimator in Bronzeville, which is the community of the microgrid, to enhance situational awareness, estimate system stats, and detect system topologies in real time. Many people debate, do you really need distribution state estimation? We think we do, and we got to work on it now, and it's well along in its development. And of course, as Neva said and Arshad said, we can't do this alone. As the slide shows, the partnerships we have 24 grants with the Department of Energy and other partners to figure out new technologies and deploying them for real on a real grid in harsh environments. So back to school, analytics is the curriculum. The next generation requires grid edge sensors that are hooked up in many ways to fiber, and we see these changes across all aspects of our grid. So we're moving the model where smart becomes standards. No bigger example is that in the distribution journey. If you go back to the 90s, we initially installed distribution automation on our system, and as you go through the chart that's listed here, we started expanding that to mid-circuit reclosers, which only protected half of the customers half the time, and put that on a 900 megahertz system. And then as smart meter came in, we were able to introduce loop schemes and a mesh network of control in those systems. And then as we advance today, there's been some advancements in S&C post-closing and G&W, our partners, and now we're moving to even more advanced schemes that I will demonstrate here on the talk using fiber as a connection point. So let's go through a quick little example of traditional protection and restoration schemes that's listed there. So you have a fault that happens in the middle of feeder. You have a lot of angry customers that go off, and you see in the bottom left there is a solar installation that they go offline, and the devices operate and interrupt the majority of feeders. There's triebacks, automatic triebacks that occur to see if the fault is transient, and that opens up again. There's another tryback that opens up again. We try it again. Now we begin the restoration sequence, open up the devices closest to the fault, and then restore from the loop end and back from the source. That's today, or we might call that traditional. But what does that really do? A few takeaways. It introduces significant momentaries in the system. And the peer-to-peer radio mesh network operates at 900 megahertz and is oftentimes can be unreliable, and it's up to only 1 watt of power, which reduces the peer-to-peer communications on that. And later we'll see how we're working to improve that. Of course, we go send the truck to fix the problem. So the future. What is the future scheme? Well, we have advanced distribution schemes. This is all interoperable using the existing equipment we have. Different vendors, all interoperable. Let's start with our fault here that occurs. Well, these arrows here is basically IEC 61850 goose messaging. They're talking to the devices peer-to-peer at high speed on fiber, goose messaging, IEC 61850, and they're changing the time current curves on the devices. They're changing them in order for the renewables to stay up and for all the customers that are on the front end of the feeder to stay on. So we try back the circuit. The fault is still there, but the devices are still communicating and changing the time current curves of the other devices so that the customers stay on. We do it again, and again, we change the time current curves through fiber, through goose messaging to keep the rest of the customers on. And then we begin the restoration scheme. You know, we restore, we isolate the fault, we store the back end, and we send the truck to fix the problem. A few takeaways on this. The DER remains connected to the system. We continue to expand our philosophy of using the same time current curves for all DEA devices. We have faster tripping and reduced arc flash current. With this deployment of fiber and these clearing schemes on the system to integrate renewables, we will reduce arc flash energy by 50% on the distribution system. We will introduce transmission clearing times onto the transmission system and reduce momentaries from about by about 50% and a 58% reduction in DE trip times. So that's an example. So where are we going in the future? Smarter grid solutions. We have our sensor layer, our platform layer, and our application layer, as you see. And this is how we're thinking of the future. And I'd say many of these we've been applying for real on the grid, where it's in the middle, our PMUs, our distribution state estimating, our analytics platform, and of course the application layer. And this is how we view this. What's next for the smart grid? A whole bunch. Okay, a whole bunch of technology, resilience enhancements, intelligent asset monitoring, and of course fiber deployment, DER proliferation, next generation grid planning, going from a couple of hours a year of peak planning to 8760, which is the hour for 365 days. So a lot more to come. Can we make it all work? Electric utilities hold a unique position in the world as the group that makes these things work, because a lot of them don't work right away, especially in harsh environments on a real power grid. And it's all upon a lot of us to make these technologies work and deliver the future that we imagine. Thank you very much.
Thank you, Mr. Donnelly. Well, I may be the one of the person who introduced the smart grid concept to Korea. It was exactly 10 years ago. You are the Google search, the Google search frequency is exactly coincided with that time. At that time, I have to make about 140 lectures outside the university. So I stayed more time in the outside school, but now I go back to the university school again. Thank you for explaining clearly for the situation. And the next speaker is the Professor Mark Glick. He is the specialist on energy policy and innovation at Hawaii National Energy Institute. Thank you.
Thank you, Professor Moon, and I also want to thank KEPCO for the great honor to be here today, and of course to be part of this esteemed panel. Really extraordinary. I also echo Terry's comments on the recent tragedy, and our heart goes out to you. But before I get into the discussion, I wanted to briefly introduce you to the Hawaii Natural Energy Institute. We're part of the University of Hawaii at Manoa, and we are an organized research unit there that is really dedicated to support Hawaii's energy transition, particularly from the technology and analysis viewpoint, and making sure that that fits into the policy agenda effectively and that the policy intent is met. We are one of 3 entities that had been set up by statute. We were founded in 1974, but we became part of statute, state statute in 2007 to carry out our mission, along with the Hawaii State Energy Office, which I led previously for 5 years, which handles the energy policy and planning and supports driving the policy agenda, as well as the Public Utilities Commission, which we know is the oversight agency of the electricity sector. I also want to provide some context as we talk about the role of microgrids in Hawaii's energy transition and essentially how we got there. You know, it all started about a half century ago with the wake-up call that I think the entire United States had after the Arab oil embargo and the enormous price volatility and how it wrecked the economy. And I think many world economies suffered it, particularly in the West. We decided that we needed to become energy secure, and we did that through our principal driver, a renewable portfolio standard. And that's essentially setting the goal of how much renewable energy we would replace the oil. And that began with a voluntary RPS in 2001, expanded to the first mandatory one in 2004. And in 2015, after considerable progress, we became the first state in the nation to set a 100% renewable portfolio standard. We also have an energy portfolio standard, and we also provided funding to support this through Act 97, our Food and Energy Security bill. But by 2018, we also saw, and I think there was a lot of frustration in the Hawaii legislature that we weren't making enough progress on building a more resilient system, particularly through microgrids. And so Act 200 was passed, and we'll see how that fits into the overall agenda. Once these bills were passed, we actually had to execute on deploying clean energy. And our challenge in Hawaii is that we have 6 independent grids that we have to manage. These are not connected by submarine cables. They're not entirely supported by renewable energy where, for example, on Oahu, a 1,200 megawatt grid isn't expected to have all the energy it needs on shore to be able to renewable energy to support our million person population. So it presents significant challenges. We also have to deal with land use and community acceptance and so on. So our agenda is really driven, and I think the role for microgrids, particularly in a remote and isolated location like Hawaii with these independent grids, becomes even more important. As we've learned from Professor Moon and the great work at KEPCO, in places, and particularly urbanized places, Korea and the major cities, very, very low number of outages, high reliability of energy. But in these remote locations, you can have brownouts and a much different environment. So that's part of why the microgrid policy moved forward. After Act 200 was passed, a microgrid services tariff process through a regulatory proceeding, 2018-0163, was set forth by the Public Utilities Commission. We became the second state in the nation to try to arrive at such a tariff. Now, we didn't take on a more complex type of tariff that would deal with a hybrid microgrid, one that would require the use of utility assets among many different metered locations. We simply wanted to look at a simple microgrid, and that's what was taken on in phase 1. That did, I think, sort of set the policy or set the expectation that we could only take on certain kind of microgrid projects in Hawaii initially. I also wanted to point out that our microgrid adventures are also, we take into consideration the fact that we have high degree of expectation that we're going to meet our renewable portfolio standard goals. And a recent study that HNEI did demonstrates that even in Oahu, our biggest challenge with the most population, that by 2030 we'll be able to achieve 70% clean energy or 70% renewable energy with the phase 1 and phase 2 PV and battery energy storage systems that have already been approved through the use of about 650 megawatts of firm power with very low amounts of curtailment. So we have a great deal of expectation that we're going to be able to move forward. So now we need to address the issue of resilience. And what does resilience mean? We took a look at, there's 4 sort of indicative microgrid projects that HNEI has taken on in Hawaii. The Coconut Island microgrid is looking at AC and DC systems along with vehicle-to-grid integration. But I'm going to focus on the other ones. The Natural Energy Laboratory of Hawaii projects, there's 2 listed there. One's a planning project, and the other one's a microgrid development project that I'll mention in a moment, as well as the Molokai Clean Community Energy Resilience Action Plan, a community-driven energy plan. I also want to give kudos to the international program that was established here in Korea and managed by KTEP. And I have to really extol the virtues of the vision of the MOTI minister, Young Won Ju, who secured this funding to essentially double your RD&D funding in Korea from $500 million to $1 billion over the course of 5 years. It was a very real and significant investment, part of what Secretary of Energy Ernie Moniz under the Obama administration had developed and had spread among 24 countries throughout the world to support this kind of additional RD&D to make a real difference on climate change. There was a call for projects, and we answered that call working closely with Seoul National University, and we were able to put together a consortium led by a local company, Encord Inc. out of Seoul. LG joined, as I mentioned, Seoul National University, Gwangju Institute of Technology, Science and Technology, HNEI, and of course our Natural Energy Laboratory of Hawaii. And the resilience need here that we were trying to resolve is that there's a farm compound in this ocean-oriented industrial park, and coming from 3,000 feet underwater is seawater to support the kelp development necessary for the abalone that's grown there in a farm. And if that's ever interrupted, the abalone dies. So this microgrid was meant to ensure uninterruptible supply of water, of seawater, for that. And it has a lot of really interesting technology elements to ensure cold start, so there would be a rapid ability to be able to respond to outages, and the way that the outages would be contained through renewable energy at that location. And I think you can see from this particular grid, our challenge, we kept the microgrid plan very simple because, again, the microgrid tariff that was developed under the Microgrid Services Tariff docket only dealt with a non-hybrid microgrid. So we kept the focus on this simple system. It's located in this map near where the yellow circle is. That shows where the where the PV arrays are being, and the batteries are being installed. That's where the 255-inch lines from the seawater, the pumping system that this microgrid support are. But we originally wanted to include that central area, which is the research campus and the administrative buildings. Also included in that is a hydrogen fueling facility. And then the green areas at the top is the broader farm compound. We passed on trying to make that more complicated microgrid, again, because the tariffs and the regulatory structure to approve such a complex microgrid were not in place. We are currently working on that, and hopefully we can come back and do a more complex microgrid. But I think one of the more fascinating programs that we've recently done is to take on, at the request of the community of Molokai. It's an island, mostly Hawaiian ancestry, and about 8,000 people, relatively small grid, peak power at maybe 8 megawatts. It normally operates around 5 megawatts. However, for the people of Molokai, resilience means uninterruptible service of their fire, health systems, dialysis for the elderly, and also recreational centers, education. When we went in to do the planning to help them model essentially the production cost and the system stability, essentially like a mini integrated grid plan, because they were a little frustrated at the slowness of the utility to provide a renewable energy plan for Molokai. What we asked was what do you want to see Molokai be in the future, and then how does your energy system help you get there? The utility plans typically look at a very narrow focus of what's a reliable system and what's the least cost to get that reliable system in place. So this plan somewhat differs from that, and ultimately what we've decided to do is, instead of have a central solution at a power plant that's in a flood inundation zone, we will have 6 microgrids by combining their 10 circuits and making that a consolidated system to be able to cover very specific elements of their critical services that they want uninterruptible. So this is a very fascinating program. We hope to have that completed by the first quarter of 2023 and be happy to report back on that. Now, all of this is within the context of a system, as I mentioned, where we're meeting our RPS goals and we're exceeding them. Hawaiian Electric actually, in their latest sustainability report, shows that they have reached 38% renewable in their entire system. And fascinating enough, on the island of Kauai, it currently has 70% renewable energy. So, and it has a plan to get to beyond 80% with pumped hydro system that's going to be developed over the next 5 years. So the microgrid systems we see is adding this additional component of resiliency, which will be extremely important as we finalize and pursue our energy transition. Look forward to the panel discussion. Thank you.
Thank you. As you know, the state of Hawaii is the first state who declared carbon neutral in the United States. The president, the Professor Glick, played a big role for that, the plan. The last speaker is the Dr. Cheol-Hugh Lee. He is the Vice President of KEPCO Grid Planning. Let's welcome him.
Yeah, thank you for inviting me to the panel discussion. And this time I will briefly mention the difficulties ahead of us from the perspective of the power grid and how to overcome them and share the case of Korea. In order to achieve carbon neutrality, we expect significant technological and institutional challenges. On the supply side, especially the countries are setting ambitious targets for the very high penetration of renewable energy. The uncertainty and the intermittency of renewable energy make real-time balancing very difficult. I dare say that we are at the beginning of the age of uncertainty. What does that mean? Another of the most important uncertainties is load growth. On the demand side, electrification of transportation, cooling, heating brings significant challenges too. Rapid growth in the air conditioning, electric vehicles, semiconductor industries affects the load. The residential load pattern varies greatly depending on the charging and discharging of the electric vehicles. Especially the recent growth of data centers is also expected to have a serious impact. As shown in the picture on the right side of the screen, the global energy mix is projected to shift rapidly towards power and hydrogen. The share of electricity and hydrogen in final energy consumption is now only about just around 20%, and it may grow to 50% by 2050, according to McKinsey's survey on 2022. The important thing is that these all changes in energy consumption eventually turn into new laws. How quickly and how extensively widely will this electrifications takes place? There are many other factors to consider: investment costs, power market regulation, technological advances, and environmental issues are increasingly important too. Let's take a moment to see what changes the past and the present. First of all, the type of power source is changing from nuclear or coal-fired power plants to renewable energy. How do we express renewable energy? As written on the screen, it is expressed as a distributed energy resources or an inverter-based resources. It means there are huge technological differences. Especially the expression distributed energy resources once made us deluded because of the feeling of being evenly distributed across the country. Some of us thought that the new era of no more transmission lines would come soon. Now, no, we don't talk like that anymore. Traditionally, according to Korea's base plan for long-term electricity, power supply and demand, generation expansion plan was first proposed, and then transmission expansion plan established by KEPCO. However, the status is changing to the extent that transmission expansion plan must be established first or considered together to resolve uncertainties in renewable energy penetration. Reliability is a very important factor. It's been particularly important in the field of infrastructure, which cannot be judged solely by only economic feasibility. However, considering recent international trends, energy security is an issue that is emerging as important as reliability. So the approach to transmission planning is changing to address the uncertainty issues mentioned earlier. Let's take a look at how KEPCO changes. The first is that the various scenarios are being considered. How do we consider the location and capacity of the renewable energy? What will be the share of nuclear power? And how the energy mix will change, where, when, and how much renewable energy can be installed long before the developers disclose it. Depending on which scenario to follow, the actual amount of transmission expansion required will be clearly different as shown in the figure. Directional determination may be the worst case scenario or the most probabilistic one. The second is that we are starting to apply proactive planning based on predictions. Why should we do that? In addition to the location mismatch between renewable energy and load, the mismatch between the construction of the transmission lines and the PV installation period is very large. Finally, in addition to these various technical alternatives are added, superconducting cable system is constantly being considered in addition to installing synchronous condensers to compensate the inertia. We are now thinking of the attaching flywheel to the retired generator units. Also, the ESS is also widely used. Let me skip these pages. That's because we may have a chance to discuss this one. There is a place where the issue of renewable energy is being highlighted most intensely in Korea. It's beautiful Jeju Island. Jeju Island is connected to the mainland by two HVDCs, and the third one is under construction. As you know, the Jeju Island's renewable energy penetration exceeds 18% last year, and we have a goal of achieving almost 75% by 2030. Instantaneous renewable energy supplies 60 or 70% of the power. So the curtailment nowadays is becoming a sensitive issue. The problem is that we are only in the beginning stage. To mitigate the curtailment, various techniques mentioned like this, the time-based rate, FRESS, HVDC control, synchronous condenser, minimum generation output, all those kind of measures are applied all together. Still, above all, active efforts are being made to facilitate large-scale ESS installations. Nevertheless, I'd like to say that new demands needs to be created where the renewable energy is abundant or electrically distances is very close. Efforts are also needed to reduce the burden on the power grid by decentralizing or distributing the large-scale demands, such as data centers. All those data centers in the future are concentrated only in Seoul metropolitan area. So I'd like to say that rather than relying solely on power grid, we need to find a better path altogether. Thank you.
Thank you, Dr. Lee. And Dr. Lee explained clearly what is the problem we have in Korea and what is the challenges for new grid planning in Korea. Many of the problem challenges we may show on the every countries. Well, let's finish the presentation session and move to the Q&A session. Could you show me the result of the Q&A given to the audience? What's the result of the Q&A number 1? Well, it's not ready. Could you vote for the answer? The question is this: in order to achieve the carbon neutral, renewable energy should be introduced to grid on a large scale. What is the most important work to accommodate the renewable energies? Well, while we are waiting for the answer from the audience, Professor Glick, would you show your ideas?
Oh, yeah. I mean, it's a very important question. And, you know, in Hawaii, we typically look at a portfolio approach. So we would not just do one, but the question asked for one. So we would probably, I hate to influence the answer, but we probably would start with the energy storage system, followed by microgrid. But I'm sure whatever you choose is correct.
Thank you. I made this problem by myself. I spent the whole week to make the 5 problems. See, your answer is concentrated on the number 3, energy storage devices, and I nearly think that most of them, all 4 elements should play the important role for the large scale, the renewable energies. Let's move to the question number 2. Can you show me the question number 2? And start vote. It is very interesting. In order to accommodate renewable energy, a large investment for power grid infrastructure is required. How this investment is to be made? But many countries have the same problem. I'd like to ask Mr. Dr. Pu for the comment. Yeah.
Yes, that's crucial questions for Vietnam too. Let's look at the Vietnam situation. You know, in Vietnam, up to now, the investing for power grid infrastructure is responsibility of state-owned corporations like EBN and PT. The delegation of EBN is present here. And to achieve net zero emission targets by 2050, you know, and as a result, the grid connected to the renewables, the share of renewable and the share of the investment for the grid connected to renewable energy is getting higher and higher. So in my opinion, you know, the investment on large grid infrastructure should be come from the government and the private sector combined. Government should be in charge of core transmission grid, and private sectors for the grid that's connected to the renewable, and that's what has been done in Vietnam since 2021 at the end of last year. Thank you.
Thank you. Well, more than half of the audience voted for government budget. Yet, in my opinion, at the beginning of the development, the government has paid lots of budget. But please think about this. The cost, total amount for final grid, maybe much more than the government, the budget can handle. So in my opinion, it is gradually moved to the private sector because we need a huge amount of the investment. Also for the private sector, it's a new chance for create the new business and new industry. So it is the beginning stage. The government and maybe the electrical company has to pay the investment first, but it will gradually move to the private sector. That's what I'm thinking. Well, let's move to the third question. Yeah, the question is this. What facility can make the most important contribution to carbon neutral? Well, renewable energies, transmission, distribution network, energy storage system, and also nuclear power, including SMR. I hope to get the poll. Well, I'd like to ask to the Dr. Lee, what is your opinion? Not the answer, the opinion, please.
Well, the correct answer might be the number 2 through the 4. I'm in the same position as the audience. Also, I have no doubt that the renewable energy can contribute most to achieving the carbon neutrality. Nevertheless, I think nuclear power can play a role as a bridge in terms of the energy mix for carbon neutrality. Although limited, the nuclear power have the load following capabilities, and the renewable energy penetration is not as fast as we think in Korea. So that's why I agree with that kind of the answers. Thank you.
Thank you. Yes, it's a very delicate question too. Right? See, I really think so. The renewable energy will play a big role. And in addition, the nuclear power, including SMR, new technology, small-scale nuclear power will play the big role too. But both of them has to solve some problems the electricity by themselves. The renewable energy, we need a huge amount of large land. For nuclear power, the technologies are still immature, so we have to wait for that. But anyway, the renewable energy and nuclear power, energy storage system, and TC system will play a big role for the carbon neutral network.
I think, just
go
to
ahead.
add, I think none of it works without the transmission and distribution network that has to become way more resilient, and all the associated control systems and technologies to integrate renewable energy to the grid. You know, you have to have the ecosystem. And it sounds maybe a little boring to pick that one, maybe, I don't know. But you gotta have it, and it's gotta get a whole lot better. So.
The power grid is the platform to accepting all these the elements. Thank you. Well, let's move to the fourth question. Can you show me the fourth one, number 4? The globally, which generation will be the most widely introduced in the future to achieve the carbon neutral? The solar power, wind power, hydropower, and nuclear power, including SMR. It's very interesting. Well, I'd like to ask Mr. Wani-san for the comment.
Thanks. It's a very difficult question. My opinion is that all answer correct answer, because each power source has its own advantage and disadvantages, and each power source is suitable for the situation in which it is introduced. By introducing each source in an environment where it can take the most advantage of its unique characteristics, we can achieve the best mix of power source in the power system and promote the realization of carbon neutrality. Thanks.
Any other comment from the speakers? Like I told you that it depends on the situation, because many of the audiences are Korean, so I really think that is the opinion of the Korea. Well, it's very interesting. Number 3 and 4 are a little similar questions, but the answer is a little different. It's very interesting.
Well, and I'd love to,
Go ahead,
add a comment to this, because what I think is really important, nuclear, solar, wind, hydro, I think those are all enablers of a carbon neutral grid, but you need other things for a full carbon neutral economy likely. So a suite of technologies, optionality is critical, and looking at things also like carbon sequestration is going to be a really, really important technology for the overall global economy-wide decarbonization to really enable this. So I think it's fantastic. I hope we have 42% of energy being from nuclear. That would be wonderful. I know that's not what the question is, but I do think the suite of technologies is critical, and the infrastructure that enables that is also very critical.
Thank you for your comment. Well, let's move to the last question, question number 5. How do you expect the future of the fossil fuel? It may be the easy or difficult question. It's very curious. Anyway, I'd like to hear the opinion from Mr. Donnelly.
Just waiting for the results a little bit.
Well, number 2 is majority, right?
Yeah,
I see.
my own thoughts is it seems to be number 2, and you get a feel for the technologies that, whether it's through hydrogen or carbon sequestration, are starting to make some big moves forward, and seeing that decarbonization of natural gas plants and things like that. So you do see that that role will continue. It'll be reduced. Of course, it all comes to be a matter of time. So as time goes out more decades and more years, I think it's going to be zero in the end. But it's a matter of time. What is your time frame? I think maybe in my view of a time frame, it's probably the reduced role for fossil fuels.
Thank you. Well, any other comment from the speakers? Yeah. See, I made 5 problems by myself, and I expected the answer. But some of them agree with my expectations. Some are not. It's very interesting. Anyway, it was very interesting, the cases. Well, thank you. And let's move to the Q&A individually. Well, we prepared some questions, but I think we do not have enough time to cover all the questions. So I may select some of them. First of all, I'd like to ask Mr. Wani-san. Well, when we are building the new grid infrastructure, it is very lengthy in terms of the financing and the permission, getting permission and construction. How we can accelerate the procedure? You are a very experienced person, and we hope some advice from you. Yeah.
Thanks. I would like to answer. In the case of large-scale project, such as the reinforcement of an interregional interconnection line, it is important for various parties to coordinate with each other in order to promote consensus building among various stakeholders. We believe it is important to present the national policy and grand design, as well as to support it by national policy. In Japan, the Organization for Cross-Regional Coordination of Transmission Operators, it calls OCTO, and local power transmission and distribution companies are currently working together to develop a grand design for the future of interregional interconnection lines and the regional grid to introduce renewable energy to suitable locations in order to achieve carbon neutrality by 2050. Thanks.
Thank you. Yeah, thank you for your comment. Well, the second question is this. We are suffering from the COVID-19 nearly 3 years. That affect a lot. The global supply chain has been changed. And also, that also affect the energy infrastructure sector. See, I'd like to ask to the Dr. Lee, how do you think what is the critical bottleneck and how we can overcome it? Yeah.
Well, the COVID-19 pandemic has continued almost over 2 years, affecting many fields. To make matters worse, the Russian invasion of Ukraine in the beginning of this year is shaking the roots of the international order. So it may be difficult to tell exactly what affected it, but anyway, the face-to-face meeting have decreased, and the construction management has become difficult. In many cases, it's been replaced by the video conference, such as Zoom or like that. Anyway, in some cases, the residents' consent in the construction of power facilities, such as transmission lines, is the key in the construction. But it took a long time to persuade them. That's because we were not able to meet each other. In terms of materials, I can say that most of the materials for power infrastructure in Korea are self-provided by domestic manufacturers. However, complex facilities such as relay or HVDCs equipped with semiconductors, they are severely affected by the international price fluctuations. It's not comparable to the impact of soaring fuel prices, but if it's not normalized quickly, then the infrastructure may also be affected more. For now, for the time being, I believe that we will overcome it by adding additional manpowers, diversifying procurements, and extending the life of existing facilities, I think.
Thank you. I'd like to ask to Mr. Donnelly. We think the role of government is very important. Do you think, do we have the right regulatory model which can encourage and reward the new power grid we have to develop? And if we don't, what is your suggestion to overcome it?
Well, what we've seen, especially in Illinois and in the Chicago metro area, is the regulatory models are continuing to evolve to meet the needs of the future. As many of you know, policy in this area is predominantly state-driven in the journey toward renewable goals. And in Illinois, it's mainly a legislative approach through the Energy Infrastructure Modernization Act of 2012, the Future Energy Jobs Act of 2016, and also recently the Climate and Equitable Jobs Act, which sets a course for clean energy in the future and clean energy goals. And then the regulator becomes sort of the agent to help implement the policies of the legislature carried out by the utility. I think recently we've seen some support at the federal level. Usually the federal level has been no federal energy policy, but recently the Inflation Reduction Act has provided some sweeping type of incentives across various climate initiatives that involve energy. So I think we're starting to see the gelling or the evolution of federal, state, local policies come together. What I would comment on the recent goals, our regulatory model was completely reformed, and there are performance metrics in our filings. So now there are penalties and incentives about traditional reliability, and actually reliability in environmental justice communities. So many certain zip codes about communities in need, and are you improving reliability even more and resiliency in those communities, reducing disconnects by certain percentages in certain zip codes and areas, and customer service goals, peak load reduction, SAIDI goals, have recently come out as performance metrics to incentivize performance. So we see this model evolving. Is it perfect? No, it's not perfect, but I know in Illinois and California, by the GridWise Alliance, these two states are the leaders in grid modernization. We tend to think of California. A lot of folks don't think about Illinois in the middle of the country, but we're doing some good policy. There's some good policy support, incentives for energy efficiency, and some incentives for investment and for performance. The overarching message we're hearing is who is benefiting? Who is benefiting from these investments? And it's the communities in need that need to benefit. And the policymakers are very focused on who is benefiting from these investments, not just in reliability in communities in need, but also jobs. Where are we hiring people to meet the needs of the future, and how are we educating people and reaching into our communities in need to hire folks? And about 40% of the benefits of the recent law is to flow. Of course, there's a measurement issue, is to flow to communities in need. We see that as an overarching priority in Illinois, and we see it, quite frankly, in lots of parts of the U.S. Thank you.
Thank you. Thank you. You are the wonderful comment. Well, I'd like to ask to the Dr. Phuc. I visited Vietnam several times. Even in the winter time, it was a very hot country. So due to the climate change, temperature may go up higher and higher. And in their cases, how can we design and operate the new power grid for preparing for the climate change? Can I have your opinion?
Yes, coping with climate change is the big issue. In terms of designing, constructing, and operating the grid, in my opinion, we should consider all the climate variables in designing, in constructing process. And they are, for example, temperatures, they are the wind patterns, they are drought, they are sea level rise, for example, and the flood estimation also. If we consider all these climate variables in designing, in constructing processes, it makes the designing very, very complicated and time-consuming. I think that we should work on many climate models for power system design and constructing. That's my answer.
Okay, thank you. It's not easy, but we have to tackle it, solve the problem together. Well, the last question, it may be the last question to the speakers. And I'd like to ask to the Professor Kulik, could you tell me what is the recent project or initiative that can you think is truly innovative or successful?
Yeah, thank you for that question. One of the things I spoke a little bit about the Molokai planning process, energy planning process, but it's really part of a program, or at least it came from a program called the Energy Transition Initiative Partnership Program with the Department of Energy. And HNEI became a regional partner 2 years ago, nearly 2 years ago. And we provide technical assistance to solve any key energy transition problems. So there were requests from Molokai, from Hawaiian Electric on mapping hybrid microgrids, from Kauai on mobility, transportation planning, just a whole series of things. And we found the notion of place-based place-based technical assistance, meaning having a local party like an institute like HNEI teamed with the National Laboratory System and with the Department of Energy to support that. We're still working out how that works. You know, what does the local party do? What does the laboratory do? But being able to tackle these problems and provide essentially free assistance to communities is a very exciting thing, and we're really excited and very proud to be part of that.
Thank you. It is time to close the session. 2 hours flies like an arrow. It was very valuable time to share our ideas and experience. And we can hear some successful story, and we hear more problems. When you acknowledge again that we still have a long way to reach to the carbon neutral. And also we need the brand new power grid. Carbon neutral, in my opinion, carbon neutral cannot be achieved by the specific countries. Global cooperation is essential, otherwise we may not success. On the way to develop new power grid, we have to solve not only technical problem, but also political and economical problem too. However, we are not alone. Share our ideas and our experience. And let's move and change proactively. Thank you.
Thank you. Thank you very much for our moderator and also the panelists for the insightful information. So we have listened to presentations and discussions regarding 2050 carbon neutral strategy and future grid insights in the presence of domestic and also overseas CEOs and CTOs in the power and energy sector. We would like to express our sincere gratitude to those who attended the conference today. And now we'll proceed with the commemorative photo session. And also, Vice President of Korea Electric Power Corporation, Mr. Lee Jong-hwan, please come up to the stage for the photo session. Thank you. Okay, so please look at the camera and you can remove the mask for the photo. Okay, big smile please. 1, 2, 3. Thank you. And please, let's take one more photo on the stairs because we want to include the logo in the photo. So please come down to the stage, right in the middle. And please step down in the middle. Thank you very much. Okay, now we're going to proceed with one more photo. Please look into the camera. And big smile one more time, please. 1, 2, 3. Okay, thank you for your participation. Thank you very much. So the luncheon will be held at the Holiday Inn Hotel just across the Kim-Dae-jung Center. So if you would like to attend the luncheon, please move to the luncheon hall. This was Min Hyang-jung, and thank you and have a great day. Thank you.